All right, we're picking up where we left off from last class. Last class, we just got using heat of fusion in some calculations. We're going to be continuing on with a similar theme. We were talking about intermolecular forces and a bunch of ways that we can change between, for example, solid and gas, sublimation, solid and liquid, melting, or liquid to solid, freezing. And we're going to continue on with talking about evaporation. Evaporation, of course, being liquid to gas. And when something evaporates, as a liquid, all of our particles are touchingly close. They can interact directly with each other. There's no empty space between the particles. You can't compress a liquid. You can't squeeze them any closer together. When it turns into a gas, they're all completely separated, completely free of each other. And in order to make that change, make that transfer, we have to put in energy. We need energy to separate, we'll just assume that they're molecules. It takes energy to separate the molecules because of the intermolecular forces that are keeping them together, the sticky forces between the molecules. You've experienced the endothermic property of evaporation one way or another. Most likely you felt it when sweat evaporates from your body. The sweat evaporating from your body, it takes energy to turn that liquid into a gas. So you're losing energy from your body, that's cooling you down. And if there's a breeze, that further intensifies the cooling effect. That increases the rate of evaporation, so it cools you down faster. If you've used hand sanitizer, I'm guessing most of us have, you also can feel it a little bit more explicitly there because it's a more volatile liquid, and so it evaporates at a lower temperature. So that cold feeling you get after you put hand sanitizer on, that's you feeling the evaporation, the evaporative cooling. Swamp coolers also utilize evaporative cooling. Another place where you might have experienced evaporation causing a cooling effect. If you are not so fortunate to be in a dry climate and you live in like Florida or just anywhere that has high humidity, that high humidity, you've already got a lot of moisture in the air. There's less room for the moisture from your skin to evaporate, so it slows down the rate of evaporation. And that's what causes you to feel sticky and sweaty and gross just generally when it's high humidity. Whereas us but it's a dry heat, there's lots of room for the water to evaporate from our bodies, and so we get the full cooling benefits of that evaporation. So it might be 115 degrees in the summer, but it's a dry heat. The opposite process, condensation, going from a gas to a liquid, if it took energy to go from a liquid to a gas, you have to lose energy to go from a gas to a liquid. A gas is a higher energy state. Compared to our liquid. And so we need to lose heat or lose energy. Or another way we can think of it, settle down. We need our molecules to settle down so that our molecules will stick together. If we're thinking about our intermolecular forces as a sticky force, we need them to slow down enough that they hit and the little bit of adhesion, a little bit of glue stops them and keeps holding them together. Because condensation is exothermic, heat is released. When steam condenses on your skin, like in a steam burn, it dumps out a lot of heat, more than you would get just like sticking your hand into hot water. It dumps out a lot of heat onto your skin, and that's why steam burns are so severe. It's also a contributing factor to the reason that overnight temperatures don't get as low when the humidity is high, because you've got moisture in the air. As it cools down, more of that starts to condense out because the amount of water that can be in the air at colder temperatures is lower. So it condenses out, and that releases heat into the environment, and that prevents the temperature from dropping quite as much. We don't really experience that too often. So like we have, 40-degree temperature swings, sometimes 30-degree temperature swings. If you go to the Bay Area, even if you're not right next to the ocean, it might only be a 10-degree fluctuation throughout the day. Part of that is because there's a lot of humidity. And similar to our heat of fusion, our delta H FUS, we also have the heat of vaporization, delta H VAP, VAP for vaporization. And just like for our heat of fusion, this is the amount of heat required to vaporize 1 mole of liquid, just like our fusion was melting 1 mole of our solid. For water, it's 40.7 kilojoules per mole. You don't have to memorize this, it'll be given to you. And it's a positive value for delta H because you need to absorb energy. Water needs to gain the energy in order to become a gas. It takes a lot of energy to boil water. You probably don't remember, but our delta H of fusion was like 6 compared to this is almost 41. So it's way, way more energy to vaporize it than it is to melt it. The same but opposite amount is involved when the gas condenses. So the gas loses 40.7 kilojoules per mole to condense. So that energy is given off instead of absorbed. We can use the delta H VAP, the heat of vaporization, to calculate the energy required to vaporize a given amount of liquid. We can also use it to convert between moles of liquid and the heat required to vaporize it. We should have an example of that. Calculate the amount of heat in kilojoules. So we're looking for heat in kilojoules required to vaporize 1.75 kilograms of water at its boiling point. The at its boiling point part there is just letting us know that we can use that 40.7 kilojoules per mole. For you, it's probably not that important. And we're given that the heat of vaporization is 40.7 kilojoules per mole. So if we're trying to find kilojoules and we're given kilograms, what do we need to do to make those conversions? Let's start at the back and work our way forward. How can we get to kilojoules? We could get there from joules. Do we have a number that has kilojoules in it? We do. We have 40.7 kilojoules per mole. So we can get to this kilojoules by using this heat of vaporization. That would give us kilojoules. What number, or what unit rather, would we need to get to kilojoules using that conversion factor? It's the other unit in there, it's moles. So if we get to moles, we can get to kilojoules, and that would just be multiplying by this 40.7. We'll see that when I write out the calculation later. Can we get moles of water? How do we get moles of water? What would we need to get to moles? We would need grams Can we get to grams from kilograms? We sure can. So that's going to be our set of steps that we're going to do. We're going to convert from kilograms of water to grams of water. And then we're going to convert from grams to moles, our molar mass. We could calculate it, or if we have it memorized, 18.015 is good enough, grams per mole. So those are all the numbers that we need. Any questions on how we found those numbers? Great. So starting with 1.75 kilograms. We're going to multiply by 1,000 grams per kilogram. That cancels out the kilograms. We've got 1,750 grams. We can then divide by our molar mass. And we'll get a number. It's going to be 90, maybe? 97 is the right ballpark. So 97.14 ... moles. And last but certainly not least, we multiply by our heat of vaporization. The moles cancel, we're left with kilojoules. And it is 3,953.6 ... kilojoules or 3.95 times 10 to the third kilojoules. Questions? Yeah.
Why did you set that up that you solved each one at a time?
I solved it one at a time just to be different.
Not like other chem teachers.
I'm not like other chemistry teachers. I can do it both ways. I can do it all at once or a step at a time. I just know that some people do it one step at a time, so I figured I'd do it that way for a change. Other questions? It does work if you just do the whole thing straight through in one shot. All right. A little bit of a bonus question. A drop of water with that mass condenses on the surface of a 55-gram block of aluminum that is initially at 25 degrees Celsius. If the heat released during condensation goes only toward heating the metal, what is the final temperature in Celsius of the metal block? The specific heat capacity is 0.903 joules per gram degree Celsius for aluminum. I'll give you about 5 minutes to give that one a shot. This is on the harder end of problems that I might give you. If you're feeling stuck, it might be helpful to remember that Q equals mc delta T. Well, the clock in the classroom isn't working, but that was about 5 minutes. Anyone have an answer? Any brave guessers? So there's two parts to this question. The first part, how much energy did condensing water emit, transfer? And that's the stuff that we just went over. So that's the part that you should be able to do because we just did it in the previous slide. To do that part, we need the mass of the water and we need this delta H VAP. So starting with our 0.48 grams of water, we convert that to moles with our grams per mole of water. And then we multiply by the 40.7 kilojoules per mole. Does anyone know what sign our delta H VAP should be? Should it be positive as it's written or should it be negative? Negative. It should be negative. Condensing is exothermic. So our water is releasing heat. It's also in the question if the heat released during condensation. That would also tell us that it's supposed to be negative. There's other ways that you can figure out that it's, like you can figure out the correct answer even if you don't know it's negative. It's fine. But little concept check for you. So 0.48 divided by 18.05 times negative 40.7. The water well, let's just write it. Negative 1.08 ... kilojoules. This is energy released by water. all of that energy goes towards heating the metal. It goes to heat the aluminum. If aluminum's gaining that energy, if it's absorbing that energy, what's the sign for the heat for aluminum? It's absorbing, it's gaining, it'll be positive. So the heat value for the aluminum is positive 1.08 ... kilojoules. And this is the Q that goes in the Q equals mc delta T. We were given the mass, it's 55 grams, and we were given the C value in the parentheses at the end. We were also given an initial temperature of 25 degrees Celsius. So we've got everything we need to solve for the final temperature that'll be baked into this delta T. So we're going to rearrange that to delta T equals Q over mc. That'll be our change in temperature. We also need those kilojoules to be in joules because we have joules for our specific heat capacity. Again, this is on the harder side of questions. I'll probably put one of these on the exam, but this is on the harder side of questions. This is one of those choose violence questions. I like to put a couple of those on every exam. All right, so putting in those numbers that we were given, grams and joules cancel, degrees Celsius flips to the top. Our change in temperature is 21.8 degrees Celsius. We could also make this change in temperature as final minus initial, or you can just intuit that we're going up in temperature, so the temperature is going to be added to that. And so our final temperature is going to be 46.8 degrees Celsius. We would probably round that up to 47. Questions? Do we have questions about the delta HVAP part? Do you have questions about how we used Q equals mc delta T? Yes, question.
So C is the specific heat?
Yes, C is the specific heat capacity for aluminum in this case.
Q is, what would Q be like generally?
Heat or energy. It has units of energy, but we would call it heat. Other questions? Great. Now that we're done having fun with that, some conceptual tests. This is a heating curve for ice that begins at minus 25 degrees Celsius and ends at 200 degrees Celsius. So we started with some ice cubes. We added heat. The way that this graph works is this purplish line. It kind of just looks black in the class, but this line charting from A to B to C to D to E to F in that order. This is tracking with the temperature of our water over time. On the x-axis, we have time. You can also think of this as heat added. So like we have it in a pot on a burner or in a closed container on a burner on the stove. And over time, the temperature goes up. The temperature is on the y-axis in degrees Celsius. So figure out what states of matter we have for water at each of those line points. So between A and B, what states of matter do we have? Between B and C, what states of matter? C and D, and so on. Let's start with A to B. What states of matter might we have between A and B? We're starting at minus 25 degrees Celsius. We're going up to 0 degrees Celsius. What state of matter exists there? Solid. We would have ice. Are there any other states of matter that we would have in significant amounts at that temperature? No, probably not. It would just be solid, ice. And then from B to C, what's happening to our temperature during this stretch? It's staying consistent. Why is it staying consistent? What's happening during that B to C? The ice is melting. So we have ice. As the ice is melting, what state is that going to? So we've got solid. We also have liquid. And the reason that our temperature line is flat here is all of the energy is going into melting. All of the energy is going into melting the solid. So like if you have ice water, it's locked in at 0 degrees Celsius. As long as you have ice in there and it's well mixed, it's always going to be 0 Celsius, at 1 atmosphere of pressure at least. So then we get to C, and the temperature starts going up. What does that mean that we have between C and D if the temperature is increasing? What temperatures do we have here? We're going from what temperature to what temperature? 100. What state of matter for water exists there? What state of matter is my coffee in? Liquid. So that I can drink it. So what happens at C is ice is completely melted, and because it's completely melted, now our energy can start going towards heating our water again. And so that's why the temperature rises. Then the temperature hits 100 degrees Celsius. What's important about 100 degrees Celsius? Yeah, water boils at 100 degrees Celsius. And so from D to E, this very long stretch, what's the process happening here? Yeah, we're evaporating. So we've got our liquid, and we also have the gas. And this section is a lot longer than our B to C section because the delta H vap, that 40.7 that we saw on the previous slides, is a lot bigger than the 6.02, the delta H effusion for water. It takes a lot more energy to boil the water to turn it into what state of matter from from E to F. Gas. Questions about that? There's a possibility that one of these graphs will be on the test and you'll be asked to identify a particular part, just to see if you can read graphs like this. As much as I'm sure that you would all love to do this question because it's very long, I'm going to just skip it if that's fine with you. The basic idea is we're working on, I think it's this transition from A to D, this sort of a transition, and you have to calculate the heat for each of those three lines separately and then add them together. So that's why this ends up being a really long problem. You can ask me about it in office hours or after lab if you'd like.
Is there a chance it will be on the test?
I don't remember if I put one of those on the test most of the time. It would be a fair question to ask. All right, any questions about intermolecular forces changing between states of matter? It's a little bit sad that this is now baked into this chapter because it used to be that this was its own chapter and I could start the class off by saying, you've got problems, I've got solutions. And that always got a couple of laughs. I still got away with it, but a little bit less fun. So we are starting to talk about solutions, which is great because we're going to be doing some stuff with solutions next week in lab. A solution is a homogeneous mixture. It's a mixture, so therefore it's two or more substances. What does homogeneous mean? Yeah, the homo part meaning same, homogeneous, the same consistency throughout. Like homogenized milk that you buy at the grocery store, you don't have like the fat layer at the top. It's the same consistency throughout. Thank goodness for that, right? Okay, solutions are common, super, super common. They're all around us. They're in us. Most of the things that we encounter in everyday life are solutions. The ocean is a solution. It's a mixture of salt and other solids, some of them coming from fish, dissolved in water. Our blood plasma, take out the blood cells, is a solution of several solids and some gases, also dissolved in water. Just to name two examples of solutions. Coffee is also a solution. It's a solution to being tired, and it's also got a bunch of dissolved solids in it. There are many types of solutions. If we look at our definition, it's a homogeneous mixture of two or more substances. It doesn't specify that it's liquids or gases or solids. It can actually be all three of those. So an example of a gas dissolved in a gas, not in that order, is air. There's a bunch of different components in air that we breathe, that we need. Some of them are bad also. You can also dissolve gas into a liquid, like in carbonated beverages. You can dissolve ethanol into water, like in alcoholic drinks, some of us might like to enjoy. You can dissolve solids into liquids, like with salt water, and so on and so forth. A key part of solutions, the homogeneous mixture, is that we have at least two components, otherwise it's not a mixture. And those two components are the solvent, which is the majority component, and the solute, which is the minority component, the smaller component. Most of the time, usually, solvent refers to a liquid. That's what this second point is about. In a solid liquid solution, like salt water, like coffee, the liquid is considered the solvent regardless of how much we have. So you can also use solvent just to mean the liquid part. Our most common solutions have water as the solvent, and we call these aqueous solutions. So the aqueous part means that we have a water solvent. Again, it doesn't matter how much water we actually have. It could be that we've got less water than the solid that's dissolved in it. We would still call that an aqueous solution. You can also use other solvents. For example, if you have nonpolar solutes, water is notably polar, so it's not going to dissolve nonpolar solutes like fats and oils. Big takeaways: you need to know what solvent and solute are, and you should have already known that aqueous solutions have water as their basis. We've heard this phrase before: like dissolves like. This means that polar solvents dissolve polar solutes, and nonpolar solvents dissolve nonpolar solutes. Some common polar solvents include water and acetone and methyl or ethyl alcohol. Methyl alcohol is often called wood grain alcohol. Ethyl alcohol is often called a good time. And our common nonpolar solvents include things like hexane, ether, and toluene. I would say the most important ones that you should know is that water is a polar solvent, and you could maybe recognize that hexane is a nonpolar solvent. When we dissolve something in water, when we're creating a solution of solids dissolved in water, there are a bunch of factors, a bunch of things going on when we try to dissolve a solid. So we've got some water molecules represented here on the top. And we've got a sodium ion and a chloride ion representing table salt. So we've got our water represented up top. We've got our solid salt represented down below. There's competition between the forces between the water and the solid, the ions in the solid, and also between the water and other water molecules, as well as between the sodium and the chloride. In order for us to pull apart the sodium and the chloride, water has to have a strong affinity for these ions to be able to pull them apart. It also has to not like itself so much that it won't associate with sodium and chloride. So our water here is our solvent, and our solute would be our sodium chloride. So these attractions between the water and the ions must be stronger than the interaction between the sodium and the chloride. Otherwise, it's not going to be able to pull them apart. In the case of sodium chloride, that's true. So you can dissolve sodium chloride or table salt in water. not all ionic compounds are soluble in water. So calcium carbonate, for example, the calcium and the carbonate have a very strong attraction to each other, and water is just simply not strong enough to pull them apart. So the calcium carbonate stays intact. And so for the most part, it stays as a solid in water. There are many, many other examples of this. Questions so far? The way that a solid dissolves in water, if we have sodium chloride, which we know dissolves in water, the water molecules are polar. They've got poles. They've got a negative side and a positive side. And they're going to surround the sodium and the chloride with the part that complements, the charge that complements. So for the water molecules, the negative side, the oxygen side, is going to buddy up with the sodium ion because it's positively charged. So the negative and the positive interact with each other, and that helps stabilize the sodium ion. The chloride ion is going to buddy up with the partially positive hydrogens, and those will stick together in solution. In water, ions are surrounded by water molecules. You should know that ions exist in this sort of an arrangement with lots and lots of water molecules all hanging out around them. If you've seen Toy Story, there's a scene in Toy Story at Pizza Planet where Buzz Lightyear hops into the claw machine, and all of the little green men are all crowding around Buzz Lightyear. That's what's going on here. Our sodium, our chloride, those are our Buzz Lightyear, and the water molecules are our LGMs, little green men. That's kind of the big takeaway, I think, here. Here's another representation of that. When we dissolve sodium chloride, this is how it would exist as like a big block. We dissolve that in water, it separates all of the ions. Usually we don't draw in all of the water molecules because it would take up a lot of space. And also I didn't want to put them all in when I was making this. So I didn't. But you need to know that they're surrounded by little water molecules. And that helps spread them out. A sodium chloride solution, represented in an equation as NaCl with the little AQ after it, doesn't contain any NaCl units. What's actually in solution is Na plus and Cl minus. It's completely dissociated. Just like if somebody's telling you something that they've told you 50 times before and you're just done and tired of listening to them, you zone off, you go completely into your own world, you've dissociated. There's no sodium chloride in this. You fully separate yourself from the situation. So we could also call that fully dissolved or separated. And we would call that a strong electrolyte. So strong fully separates or dissolves. The electrolyte part of that just means that it forms ions. This brings us to our fourth intermolecular force. Which is the ion dipole force. The ion dipole force exists when we've got mixtures of ionic compounds and polar compounds. For example, salt and water. So the ion part of this talking about the ionic compounds, the dipole part of it talking about polar compounds that have the dipole-dipole force. And we've already seen the second and these diagrams before. Ions are conductors. That means that if you put them on a train, they'll turn the engine on and take you to where you need to go. That's the other type of conductor. This type of conductor, we're talking about electricity.
I'm going to outbear you on that. I don't think the conductor starts the engine. I think the engineer starts the engine. The conductor just makes sure that there's no roam passengers on the train.
I'm willing to take that criticism because I don't know that much about trains. So here's a fun fact. Pure water does not conduct electricity. You have never experienced pure water. You've never seen pure water. You've never been in the vicinity of a substantial amount of pure water. So in your experience, all water conducts electricity. It's really hard to get close to pure water. But pure water, if you were able to get enough of it together, it wouldn't conduct electricity. The thing that conducts electricity is the ions. Ions in solution, dissolved in a solvent, conduct electricity. That's what allows electricity to flow through water, is the ions. Without the ions there, there's nothing to conduct the electricity. The water won't do it. If you get a strong electrolyte solution like KCl, which is similar to NaCl, that's going to allow for the conductivity of electricity. So electricity would flow relatively well through that solution. So this brings us to electrolyte solutions, things that conduct electricity or have dissolved ions in them, like Gatorade, and non-electrolyte solutions that don't conduct electricity. Electrolyte, for all intents and purposes, is the same as ions. Electrolytes conduct electricity. Non-electrolytes do not conduct electricity. They contain dissolved neutral particles. Because they don't have charge. In theory, you could get pure water and fill up a bathtub with it, and you could safely make toast in the bathtub.
How does one acquire pure water?
You don't. In theory, you could, though. In a perfect world, you could make perfectly pure water, and you could safely make toast in your bathtub, assuming that you were perfectly clean and you didn't, leach electrolytes into the solution. And if the toaster fell into the water, it wouldn't conduct electricity, and so you wouldn't electrocute yourself. In reality, you're not going to be able to get pure water, and so you can't make toast in the bathtub safely. You have to make the toast and then take it with you to the bathtub so that it can get soggy while you eat it in the warm bathtub, presumably a warm bathtub. Silver nitrate in solution dissolves, and it's a strong electrolyte solution. What does it mean to be a strong electrolyte solution? It's not just that there's a lot of ions. It's related to that. That's the electrolyte part. So the electrolyte part means that it conducts electricity. The strong part means that it completely dissolves or completely dissociates. And so when silver nitrate, aqueous, is in solution, it doesn't contain any silver nitrate units. It dissolves completely to silver ions and nitrate ions. And another important point here is that when our compounds with polyatomic ions dissolve, they stay intact, generally speaking. Silver chloride, however, does not dissolve in water. So like we said earlier, not all ionic compounds dissolve in water. Silver chloride is one that does not dissolve. And so we get a block of silver chloride just sitting in our water, not doing anything. We already talked a little bit about aqueous solutions. They're a homogeneous mixture of substances. When compounds dissolve, they usually dissociate into their component ions. Review again. And you can stir sodium chloride into a glass of water. It looks like it disappears. It's still there. You can taste it. You can taste that it's there. You can tell. The degree to which something dissolves in water is called the solubility. We can talk about it qualitatively, so like saying it's hot outside or it's cold outside. Those tell us some general ideas about what the temperature is relative to maybe our body temperature. We can do the same thing with solubility. We can say that it's soluble, it does dissolve in water, or we can say that it's insoluble, that it doesn't dissolve in water. In reality, it's not a binary. It's not either it does dissolve or it doesn't dissolve. There's some gradient in there. And so when we're talking about things dissolving or being soluble, that means that lots of it dissolves. And it's sort of a relative term. If we talk about something being insoluble or not soluble, not much dissolves. In reality, some of it does dissolve. We're not going to really go into the extent too much in this class. But generally, one of the ideas that I want you to take away from this is that there is a little bit that dissolves. It's just that it's not very much. And for ionic compounds, we have solubility rules, empirical rules of solubility. They're summarized in some tables in the book, also on the green sheet. that you probably have a copy of. And there's lots and lots of exceptions. Here is one example of what solubility rules might look like. This is the one that's from the book that's online. So looking here at our table, we've got in the top things that are soluble in water. All group 1A and ammonium salts, so anything that has lithium, sodium, potassium, rubidium, cesium, all of our alkali metals, those are all going to dissolve in water. And we've got some important exceptions. So if we have one of these exceptions, that means it's not going to be soluble. For our group 1A and ammonia salts, or ammonium salts, there's no exception. So if we have sodium or potassium, we expect it to dissolve. We can do the same thing for nitrates, NO3, chlorates, perchlorates, acetates. Those also have no exceptions. When we get to sulfates, sulfates would be things with SO4 in them. SO42- is sulfate. Those are generally going to be soluble unless they're paired with calcium, barium, strontium, or lead-2. So these are not soluble. This is slightly different from the solubility table that shows up on your green sheet. And then in this second table, we've got things that are not soluble. Here it's written as sparingly soluble to convey that idea that a little bit of it dissolves, but we would generally consider it to not be dissolved. So things that are in this group, hydroxides, for example. Hydroxide is OH-. So things that have OH- in them we would consider to be insoluble. They're not going to dissolve. But we have some exceptions. So if it's got one of these exceptions, then it is soluble. So for group 1A, we saw up here that those are always soluble. So if we've got group 1A, it's going to be soluble. Ammonium, also always soluble. And if we have barium, strontium, or calcium, those will also be somewhat soluble. So BaOH2, we would consider soluble. This is different from the one that's on the green sheet. I will typically give you the green sheet version or something similar to it on exams rather than this one, so you don't have to know the names. Do we have questions about this table so far? You need to know how to use this table to answer solubility questions. Need to know. Green sheet solubility rules. Okay. So those solubility rules give us that qualitative description, like hot or cold. It's hot outside, it's cold outside. For some people, that'll be different, what we mean. So that gives us a general idea, a basic idea of whether they're soluble. Ionic compounds, like calcium carbonate, that's the one we saw earlier, are insoluble because the ions are attracted to each other a lot. They really stick together, and so if you try to get water molecules in there to pull them apart, the water is just simply not strong enough to pull them apart. Molecular solids may also be soluble, depending on whether they are polar. Polar solids generally dissolve in water. Because water is polar. Polar dissolves polar, like dissolves like. That phrase that we had before. All right, for each of these compounds, determine whether it's soluble or insoluble, and we'll go over them quickly at the end. You can also use your green sheet if you'd rather use the solubility table on there. Let's do the first one together just because we haven't done one together. So CaS, we've got calcium, we've got sulfur. Those would be calcium 2 plus, sulfur 2 minus. We would call that sulfide. So we're going to look through the left column to see if we find either of these. Does anyone see anything about calcium in this left column, or maybe group 2A? There's nothing about calcium, so we look for the other one. We look for the sulfide, the S2 minus. Do we see sulfide anywhere in this left column? Yeah, we have all sulfides in the sparingly soluble, aka not soluble. Okay, so we've located the row in this table that we're going to look for, and we should check our exceptions. So group 1A, 2A, and ammonium salts, such as MgS, CaS, BaS, sparingly soluble. We have calcium. Calcium's a 2 plus. It also shows up in that table, and so we would consider this soluble. So go ahead and work on the rest. All right, FeSO4. Is it soluble or insoluble? It is soluble. Why is it soluble? Because of the way that it is. The thing that we find for FeSO4, SO4 is sulfate. That leads us to this all sulfates in the soluble in water category. So it should be soluble unless we have one of these exceptions. We do not have one of those exceptions. And so it's soluble. How about PbCO3? Soluble or insoluble? It is insoluble. The thing that we're cluing in on for this one is the CO3. That is a carbonate. Carbonates are insoluble, and we don't have an exception for lead, specifically lead 2+. And so it's not soluble or insoluble. And how about the last one? We'll do that in orange. Go Tigers. Is it soluble or insoluble? It's soluble. The thing that we're looking at here is the NH4, which would be NH4 plus as an ion. A salt is just an ionic compound. And there are no exceptions, so it's soluble. Questions? All right, that'll do it for today, and we should be able to finish up this chapter on Thursday.